Hi everyone, I want to start out today's video with another comic from XKCD. Take a pause, read it if you want to. I encourage you to look up each of these terms that you may have heard of, may not have heard of, but we're graphing the scariness of the thing the name refers to against the scariness of the name. So the Chernobyl packet is apparently very scary name, but not a scary actual thing. Kind of interesting. It's just an interesting graph to look at, I think. We're going to cover section 6.3 today. That is orthogonal projections. Orthogonal projections, and we start out. So we can kind of see how this builds, where it's going. Let's say we're given a basis of some real numbered vector, and it's u1 through un, and that's a basis of Rn, all right? And we have y is a linear combination of that basis. And y is a linear combination of that basis. Okay? So we can write, we can kind of decompose y into two different vectors. Y equals z1 plus z2. So we're decomposing it into a sum of two different vectors where z1 is a linear combination of some of those basis vectors, of some of the ui's, there we go, and z2 is a linear combination of the rest. Linear combination of the rest, right? It kind of makes sense that we can group them like that. We're just stating it explicitly, right? If I have my linear combination c1 u1 plus c2 u2, etc., 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 I can group them together with parentheses so that some of the u's are named z1 and the rest are named z2. And we'll do that a little bit more explicitly in this first example. So we have a set of 5 basis vectors. Not only are they basis vectors, but they are in fact orthogonal. So u1 through u5 are orthogonal, an orthogonal basis for R5. And we have y as a linear combination of those 5 vectors. And it says consider the subspace of the span of u1 and u2. Right, y is a sum of a vector z1 in W and a vector z2 in W perp. So the orthogonal complement of W. All right, and so the way that we do that is we're going to say that z1 is equal to, actually, you know what, before I finish writing that down, let me write out all of y. c1 u1 plus c2 u2, c3 u3, that's a terrible u, c4 u4 plus c5 u5, right? That's the linear combination of those basis vectors. Okay, so we're going to say that z1 is equal to c1 u1, the first two vectors, plus c2 u2, and that is in the span, or let me write it this way, is in span of u1 comma u2. Right? Hopefully that makes sense. It uses the first two vectors, so it is in the span of that set of vectors. Then z2 is equal to c3 u3 plus c4 u4 plus c5 u5. And that hopefully is very clearly in the span of u3, 4, and 5. All right, so that's how we've broken it up and named our z1, z2. Now what we have to show, though, is that y is the sum of a vector z1 in W. All right, we kind of got that. And a vector z2 in W perp. Okay, so how do we know that z2 is in W perp? That's what the rest of this problem involves. Show z2 is in W perp. Okay, that is to show it's orthogonal. Oops. O-R-T-H-O-G-O-N-A-L. There we go. To the vectors in a basis for W. For W. Okay, so we take z2 dot u1 and we would say and show the work that says that that is equal to 0. And it is, in fact, equal to 0. Z2.U1 is equal to 0. Actually, you know what? Let me write down y. So Z2 is C3U3 plus C4U4 plus C5U5 dot U1. And I'm not going to take and write this step out, but that would be the dot product distributed over that sum. Do a little bit of regrouping, and you would absolutely show that that's equal to 0 because we have an orthogonal basis, right? That's what we were given right off the bat. All those u vectors, they are orthogonal to each other. So when I distribute u1 over that sum, right, it's orthogonal. Same deal with z2.u2. Oops, let me go back to purple. Z2.U2, that is also, for the exact same reason, equal to 0. And then to kind of cap it off, thus Z2 is in W perp. Boom, there we go. Okay, so that's all that we have to show in terms of work for this example. But again, just kind of thinking about how we can group the terms together in a specific way and break our vector apart into two different orthogonal subspaces, basically. Now we get to Theorem 8, which is called the orthogonal decomposition theorem. We know it's the main theorem of the section because it gets a fancy name. In this theorem, we have W is the subspace of Rn. Then we're saying each y, each vector in Rn, can be written uniquely in the form y equals y hat plus z. So there's that formula that we saw previously, where y hat is in W and z is in W perp. And then it says, in fact, if you have an orthogonal basis of W, then we've got a formula for y hat. Y dot U1 over U1 dot U1 times U1. Y dot U2 over U2 dot U2 times U2, etc. through all the basis vectors. And then z is y minus y hat. So we take the formula that we were introduced to previously and we'll give it a slightly different twist in this section. Use it a little bit differently, look at it a little bit differently. In example 2, we're given some vectors u1, u2, and y, and then the first thing they tell me is observe that we have an orthogonal basis. So if you take the dot product of u1 and u2, you do get 0. They are in fact orthogonal to each other. And so what we want to do in this question is write y as a sum of a vector in W, that is the span of u1 and u2, and a vector orthogonal to W. So we want to write that orthogonal decomposition. Therefore, we need the orthogonal decomposition theorem. Okay, so what we're going to do is we're going to find y hat first. That is y dot u1 over u1 dot u1 times u1, and then add to that y dot u2 dot u2 times u2. Okay, lots of subscripts there, and I'm not going to go through the calculation. I'll just jump to what you get. You have 9 over 30 for your first two dot products times 2, 5, negative 1. And 3, 6 for the other two dot products times negative 2, 1, 1. And that simplifies to negative 2 fifths, positive 2, and 1 fifth. Okay, so there's our y hat. Now that is our vector in the subspace W. Now we need the vector that is orthogonal to it. So we take y minus y hat, which is the original vector y, 1, 2, 3, minus what we just got. Let's see, negative 2 fifths, positive 2, and 1 fifth. And you get 7 fifths, 0, and 14 fifths. There we go. So that allows us to write y, which is equal to 1, 2, 3, as a sum of two vectors. How did I write this? The first vector is the y hat. There we go. Negative 2 fifths, 2 and 1 fifth, plus z, 7 fifths, 0, and 14 fifths. There we go. So that's y equals y hat plus z, where y hat and z are, in fact, orthogonal to each other. Okay, so geometrically, I want to show kind of just roughly what this looks like. We have two vectors, the u1 and u2, define a plane. That's our subspace W. And then we have some vector y up here. This is y. And then we project it, the orthogonal projection, into the subspace W. That is our y hat that we found using the formula. And then the z that you get when you subtract, that is the orthogonal, that is orthogonal to y hat. And this guy is z right there. Okay, so we're decomposing y into these two vectors. That's the visual of what this looks like. Now we look at a property of orthogonal projections and then a theorem. The property, which I'm just going to read, and then what I want you to do, if you want one bonus point on a test, email me in common language what this property means, and you'll get a bonus point on our most recent test. If y is in W, which is the span of a set of orthogonal vectors, then the orthogonal projection of y onto W is equal to y. So send me an email, explain to me why that makes sense to you using common non-technical language. All right, and then we look at Theorem 9, which is called the best approximation theorem. This one we will go through a proof of because it's awesome. We're going to say let W be a subspace of Rn, y is any vector in Rn, and y hat is the orthogonal projection of y onto W. Then y hat, so here's the key of the theorem, is the closest point in that subspace to y. It's the closest point. Y hat is the closest point in the subspace W to the original vector y, in the sense that y minus y hat is less than or equal to the length of that vector is strictly less than the length of y minus v for all v and w distinct, meaning different from y hat. So the proof of this theorem is kind of cool. It basically says if you have a vector and some subspace, then y hat is as close as you can get to that original vector. All right, so let's look at how we construct a proof of this theorem. Okay, proof. Take V in W, capital W, distinct from y hat. Then y minus y hat is in, or y hat minus v, excuse me. Y hat minus v is in W. Well, how do I know that? Let's draw a little picture here. Okay, so kind of the same setup as the one before. I'll probably add a little bit more to it. So here's my subspace W. Here is the 0 vector. Okay, I've got that labeled. Here, let's put the vector y up here, and we'll label that. That's my original vector y. I'm going to draw this for the y vector. Try that again. There we go. And then the projection into W, put right there. That's y hat. Okay, I'm going to draw that vector. And then what else am I going to add? Oh, some other vector v. Let's put v, I don't know. Let's change color and put v over here. There's my vector v. All right. So what I just wrote about, let's see, y hat minus v, that is this guy right here. So this is v in W, and the blue line segment is y hat minus v. Actually, because we're talking about length in this problem, I'm going to label that as the length of y hat minus v is the actual blue line. Now let's go back to the wordy part of the proof. We're going to say next by Theorem 8. By Theorem 8, y minus y hat is orthogonal. This is just straight up what the theorem says, is orthogonal to W, and y minus y hat, it's also orthogonal to y hat minus v. To y hat minus v. So it's orthogonal to both of those vectors. That tells me basically that we've got some right angles here. There's one there and there's one there, even though it doesn't necessarily look right. Those are both 90-degree angles. if W were a plane, it should make sense that a line that's perpendicular to one vector in the plane is perpendicular to another vector in the plane. All right, so continuing on with the proof here, we're going to say since y minus v is equal to parentheses y minus y hat plus y hat minus v, v. Okay, there's more to that sentence, but I'm going to pause on what I'm writing and point at some things on the picture. Let me erase this and fix it. That should say y minus v. Okay, let's identify where all of those vectors are in my picture. Right, we've got y hat minus v already labeled in the picture. So let's identify where is y minus y hat. That is this vector right there. So we'll label that as the length of y minus y hat, and that'll come up in the next line of the proof. And then the left-hand side of the equation, where's y minus v? The difference between y and v, well, that would just be this blue vector. Actually, let me make it green so we keep all color-coded awesomeness. This green vector is y minus v. And again, I'm going to label that with the length of y minus v, talking about the actual green line segment. Okay, so that's where everything is in our picture. And now, how do I know that that equality is true? Right, on the left-hand side, y minus v. On the right-hand side, y minus v. And I just have my minus y hat plus y hat. So the algebra of that hopefully makes sense. Right, I didn't change anything from the left and the right except for subtracting and adding y hat and then identifying them in my beautiful picture. All right, now the next line of the proof, since that equality is true, the Pythagorean theorem, something you've seen since like 7th grade, is now coming up in a linear algebra proof, gives this relationship. Y minus v, that length squared, is equal to y minus y hat, that length squared, plus y hat minus v, that length squared. Okay, so there is my Pythagorean theorem line of this proof. So we're using it to establish a relationship about the lengths. Okay, and then we're going to say now y hat minus v. Now, y hat minus v, that vector, or that length squared, must be positive. Must be positive. And that is because, B/C for because, y hat minus v is not 0. Y hat minus v is not 0, so it has to be a positive number because, you know, when you square something, it's definitely positive. And how do I know it's not 0? Because at the beginning of this proof, and I'm going to circle it in the picture in just a second, at the beginning of this proof, we chose v and y hat to be distinct from each other, separate from each other, so the distance between them can't be 0. Okay, so because that's not 0, that ultimately gives us our conclusion, and we're going to say, so theorem 9 holds, because that's 0, and I'll explain why. And the length of y minus v squared is greater than, or actually I'm going to flip this around. Let me flip it around. The length of y minus y hat has to be less than or equal, has to be less than, the length of y minus v. Okay, so how can I get to that conclusion, right? So in my Pythagorean theorem line, so I'm focusing up here at this line, right? If the stuff on the right-hand side, this term here is positive, right? That means that this term here has to be less than this term here. Y minus y hat plus something else is equal to y minus v, right? So y minus y hat plus some positive number. If I take away the positive number, y minus y hat is smaller than the y minus v. Okay, and that's how we get to the conclusion of that theorem. In example 3, we're just pointing out that the vector that we found earlier, this y hat vector, that is in fact the closest point in W to the vector y. In our next example, we're given a vector y. We're given some basis vectors u1 and u2, and the subspace W is the span of that set, right? So kind of the same setup that we've been looking at. We're defining distance to be the nearest point in that subspace W. So basically, the setup, it's saying that we need to use Theorem 8 and find the length of y minus y hat. So by Theorem 8, the length of y minus y hat is the distance from y to W. The distance from y to W. Since u1, u2 is an orthogonal basis, right, we can use that formula that we were introduced to. Y hat is equal to 15 over 30 times u1. That's y dot u1 over u1 dot u1 is 15 over 30, plus negative 21 over 6 times u2, y dot u2 over u2 dot u2 times u2. And when you simplify all of that mess, negative 1, negative 8, and 4. That is our y hat vector. Okay, but don't take the length of that vector. That is in the subspace W. We want the length of y minus y hat. That's orthogonal to the subspace W. That is, when you do that subtraction, 0, 3, and 6. And then the length of y minus y hat is the square root of 45, which simplifies to 3 root 5. All right, and that's the closest that you can get from the plane defined by those two vectors. That is as close as you can get to this vector right there, negative 1, negative 5, and 10. We close the section out with one more theorem. If I have a basis that is not only orthogonal but also normal, so an orthonormal basis for a subspace W of Rn, then the projection of y onto W is y dot u1 times u1 plus etc. y dot up times up. So you may wonder where all the denominators went. Hopefully, if you think about it, you can figure it out. All the denominators are 1. Okay. If U is composed of those columns, then you want those vectors as the columns of a single matrix. Then the orthogonal projection of y onto W. This is kind of a cool relationship that you can establish. Ultimately, you can condense it into a product of U and U transpose times y. So this can be rearranged to be a product of a matrix and its transpose, assuming that those vectors are orthonormal. Kind of a cool relationship there. I'm not going to do a proof of it, but you hopefully can kind of see the connection. That's the end of section 6.3. If you have questions or need further clarification, please let me know. Work on some homework and ask questions as you have them. Thank you for listening. Have a wonderful day.